Can you teach someone to think? Sure, you can teach someone to read and write and do math, but what about thinking? This was a question my father asked me that really stuck with me. Now, let's think about it for a moment. If we look up thinking, we can go to psychology textbooks and find anywhere between 3 and maybe even 30 types of thinking. We can learn about critical and analytical thinking, divergent and convergent thinking, abstract thinking, scientific thinking, philosophical thinking, and so on. And now, these different lists in different psychology textbooks will oftentimes be non-overlapping. So we clearly have a lot of thinking to do. But a new type of thinking that's emerged in the past 10 years is called computational thinking. In one of my last videos, I described about how the future of most fields is tied intimately to programming, and everybody will learn to program. And in that video, I talked about computational thinking. So in this video, I want to take a moment and dive into what exactly is computational thinking, how we can think about it, and most importantly, can we teach students to think computationally? Let's dive in. All right, first, we probably need to operationalize and define computational thinking. Now, I think computational thinking is a framework for problem solving. It is simply a set of tools that we apply to a process specifically for problem solving. Now, problems can be multifaceted and have several different aspects. I talk a lot about systems and systems building. Building a system could be a problem. It doesn't need to be some world-ending problem. It can simply be a challenge that you have set out for you. I want to build a system to do this. I want to try to find a more efficient way to do that. These are also problems that we can apply computational thinking to. So, now that we understand computational thinking as problem solving, how do we go about doing it? I see 3 distinct steps to computational thinking. Step 1, we need to define our problem and break it down into its parts. Most problems will be complex and have multiple different problems built within it. We need to break these down into small problems that we can then solve. And that's step 2. Step 2 is going to be to solve these individual problems. The toolkit we use for solving these problems are often inspired by computers. Abstraction, decomposition, logic, iteration, functions, evaluations, and the like. Recall the term computer was originally to describe a person, oftentimes women, who were tasked with breaking down a complex problem and then applying mathematical or algorithmic skills to solve that problem. Now, step 3 is going to be to take these parts of the problem and build them back up into a solution. This is where fluidity between the two states becomes incredibly important. We need to break something down, solve the problems, and then build it back up together. The parts and the whole, and being able to move in between these. Similar to how computer programming is stepwise instructions to tell a computer how to do something, computational thinking is stepwise problem solving in order to come up with a solution. Computer scientists often think in terms of input and output. And this ensures that your problem, the input, will be solved. In this case, this is the output. Now, let me tell you 2 examples of how I've applied computational thinking to some of my own projects. First, I told you before about how I identified a challenge in generating header images programmatically. First, I needed to break down this problem. Where am I going to get the images from? How am I going to handle resizing? What does text overlay look like? And so on. To break down this problem into the individual parts and then solve each one, I wrap the whole thing in a small app that then can run programmatically from start to finish to achieve the desired outcome. Now, you might be saying, well, this is just a toy example, right? This was just some early morning where I set out to try to do something that was arguably a waste of time. Does this work in real life? Well, many of you know that I'm a scientist, and scientists have several challenges, including science is slow. And when we start out on a line of investigation, we don't have any way of knowing the impact that line of investigation will have. So how do we solve this? So we've identified our problem. We want to break it down into its parts and solve these parts independently. Science is slow. Well, it's oftentimes slow because we start investigating a hypothesis that ends up going nowhere. So wouldn't it be nice if we could future-proof our hypotheses? If we had some indication a priori that this was an important line of investigation. Second, we also want to be able to know something about the possible impact that this new line of investigation might have. Well, impact is measured by connecting two things that were previously unconnected, and we call it a discovery. Well, we could measure perhaps the amount of knowledge between two disparate ideas. Many of you know about my data-driven hypothesis project. This is a project where we try to use data to come up with better hypotheses that then have a much more efficient and impactful outcome. So we take all of this, we build it together into a web app in order to try to accelerate our own scientific discovery. Now, will this work? I don't know. It's still a labor of love. But the idea is to apply computational thinking to the problems that you face in order to try to solve them. These are just two examples that I've experienced that don't quite give justice to the breadth of applicability of computational thinking. Computational thinking isn't simply computer programming. It also isn't simply data literacy. It's not about using Excel or PowerPoint. Instead, computational thinking is simply an approach using modern tools to solve modern problems. So, how can we teach computational thinking? Well, first, we break down the problem. We need to define computational thinking and the different elements of it. Second, we need to come up with ways to teach these different elements. How do you teach some of the tools of computational thinking, like abstraction, decomposition, iteration, and so on? And finally, we build this back all together to develop a curriculum that will allow students to learn computational thinking. So, how do we teach computational thinking? Well, perhaps we can use computational thinking to solve that problem. If you like this video, go ahead and check out this other one, where I talk about in the future, everyone will learn to program. Or you can check out this video, where I describe systems that we can build around our activities to be more efficient and impactful. Both of these are highly related to computational thinking. Thanks for watching. We'll see you next time.